You've probably heard of quantum computers, but what about the quantum internet? Researchers think that a quantum internet could be one of the most exciting developments in quantum technology. And now they may be one step closer, using a device called a quantum repeater. So, what is a quantum repeater? How does it work? And what might this mean for the future of quantum tech? First, some background. Classical computers work using bits, units of information that can either be 1 or 0, on or off, up or down. Not much use on their own, but put enough of them together and you can start computing. The more you have, the more complex the task you can achieve. Quantum computers use a different kind of bit, qubits. Qubits can read up or down too, but they can also be a mix of both at the same time, a superposition of the two states. This can increase the speed of some computations exponentially. But that's not the only thing that makes qubits special. They can also become entangled, a quantum property that keeps two qubits in a shared state. If you measure the state of one, you will know the state of the other. And this works no matter how far apart they are. In theory, you could entangle qubits across a room, a country, even a globe. And that is how scientists hope to unlock the quantum internet. So where does the quantum repeater come in? Well, the goal of a quantum repeater is to help establish entanglement between distant qubits. And they do this using photons. Entangling two qubits that are close together is relatively simple. Qubits and photons get entangled easily. And if you take two photons that are entangled with two qubits and measure them together, the qubits become entangled, even though they never came into contact. Photons can travel down fiber optic cables. That allows you to entangle qubits that are up to a few tens of kilometers apart. But move the qubits too far apart, and the photons can get lost. The likelihood of your qubits becoming entangled decreases the further apart they are. What you need is a relay station. Enter the quantum repeater. The quantum repeater works using the same principle. Essentially, it's a simple quantum computer with specialized qubits whose only job is to relay entanglement. First, a qubit is entangled with the quantum repeater just as before. But the quantum repeater's qubits have the special ability to hold on to that entanglement, giving a second qubit somewhere else in the world time to get entangled as well. And if two qubits are entangled with the quantum repeater, they can also become entangled with each other. In theory, if you want to entangle qubits over even longer distances, you can just use more quantum repeaters to form a chain. You could even entangle a network of quantum repeaters in advance, ready for when you need to connect two qubits in different places. What you're left with is a quantum internet. But why go through all that trouble? Well, a network of entangled qubits lets you do a whole range of things. You could teleport quantum information between qubits, or you can use them for super secure communication. Researchers could connect tools like telescopes or build ultra-precise quantum clocks. You could also build bigger and more powerful quantum computers by linking up distributed networks of qubits. Quantum repeaters could change the game, but they are not the only way to entangle qubits over long distances. If you do away with fiber optic cables and instead use highly sophisticated lasers, in theory you could entangle qubits over thousands of kilometers. Researchers in China have trialed this approach using laser-equipped satellites. They broke all records by linking quantum devices 1,200 kilometers apart. In the future, we could imagine a combination of systems A network of quantum repeaters could connect a country, and satellites could connect the world. Either way, creating a robust system to allow qubits to talk to each other is vital if the quantum internet is to fulfill its potential. And quantum repeaters could be the first link in the chain.